Homework busy? No more. At Spring Library, we explain every topic in simple way. Join the learning family and score high every day.
Question 37 states that deuterium is an attractive fuel for fusion reactions because it is abundant in the oceans, where about 0.015% of the hydrogen atoms in water are deuterium atoms. Part A asks, how many deuterium atoms are there in 1 kilogram of water? Maybe we'll do part A first, then we'll talk about part B. So how many deuterium atoms are in water? In 1 kilogram of water. So we know that the number of, first we can find the number of water atoms. How many molecules of water are there? Not water atoms, that doesn't make sense, of course. The number of water molecules in water. So if you think of the mass of the water over the molar weight of the water multiplied by Avogadro's number, we can find the number of water molecules, and based on that, based on this relationship, we can find the number of deuterium atoms. So we'll do this first, and then we'll figure out how to get deuterium from that. So in 1 kilogram, there are 1,000 grams of water. The molar weight is, well, we have 2 times the mass of hydrogen, 1.007, we'll say, plus mass of oxygen, 15.99. This is all grams per mole. And we multiply that by Avogadro's number, 6.022 times 10 to the 23. We'll say molecules per mole, because we're generally, it's anything per mole, right? So this time it's molecules. So multiplying this through, we would find in 1 kilogram of water, there are 3.35 times 10 to the 25 molecules. So we know the relationship between deuterium and water, but first thing we know is that, well, hydrogen, for every 1 molecule of water, there are 2 molecules of hydrogen, right? So H2O. So we know the number of hydrogen is 2 times NW, but therefore we also know the number of deuterium atoms is the ratio given to us. It's 0.015%, so that's 0.00015, that percent ratio, times 2 times NW, the number of water molecules. So therefore the number of deuterium atoms is given by this relationship, and we find that there are 1.0 times 10 to the 22 deuterium atoms. So deuterium atoms. Great, that satisfies the question for part A. Part B, if each deuterium nucleus produces about 7.2 MeV in a fusion reaction, how many kilograms of water would be needed to supply the energy needs of the United States for 1 year? I forgot to include that in my initial givens. So the total energy then would be 1.1 times 10 to the power 20 joules. Great, so we know that this total energy that's given to us, we can represent that by the ratio of the amount of energy per nucleus, or so this is the energy per deuterium nucleus present. If we multiply that by the number of deuterium atoms, we should get the total amount of energy. However, we're asking for mass of the how many kilograms of water. That's our final goal here, right? So while we can find the number of atoms, we know that we need to solve, again, this number of atoms was for 1 kilogram of water. So in this scenario, we don't want to know just what we found for part A. We want to find out how many kilograms. We'll call X kilograms times ND, which I guess is my variable. So number of deuterium particles, well, the energy per deuterium atom is this value here. So if this value was for 1 kilogram, This, including this x term, is the number of kilograms that we want. So based on this, we can rearrange if we want to solve for x here. We have our total energy, which is given to us in the question, our energy per deuterium atom, which is given to us as well, and multiply by the number of deuterium atoms, which again is given to us. We can simply solve for x. If we plug this in, the total energy, 1.1 times 10 to the 20 joules. We divide this by the energy per deuterium, again given to us, 7.2 MeV over number of atoms, and D will say, well, we don't want MeV, we need joules to match our numerator, so multiply this by 1.6 times 10 to the negative 13 joules per MeV, multiplied by our number of atoms that we found in part A, 1.0 times 10 to the 22. I'll say ND, counting number of deuterium atoms, double checking our units, ND would cancel, MeV cancels, and joules cancels. So I guess one term in our denominator should have had, right, sorry. Our ND is this many atoms per kilogram. Right, ND per kilogram. So we are left with our denominator has 1 over kilograms, which gives kilograms. And multiplying this out, we find that the total mass in kilograms for x here would be 9.6 times 10 to the 9 kilograms. So the trickiest part of this question, well, not the trickiest, but some tricky parts where we find the number of molecules of water, you need to convert that to hydrogen and therefore then to deuterium, because there's 2 hydrogen per water, and 0.0015 times that for deuterium. And recognizing that this value above is actually per single kilogram, we can solve for the number of kilograms, which we call x, based on this relationship. And there we go.